Okay, good morning, everyone. Thank you, Mary, for arranging me to give a talk at this very sad and important meeting. Before my talk, I would like to extend deep condolence to Professor Rodney Baxter's family. I also wish to recall the enjoyable moment I shared with Rodney during my 10 years at NU. And I like to see he was a great yet approachable professor. I still remember not long after I joined Mary's group as a research fellow in February 2003, Rodney invited his French female postdoc and me to dinner at his house on a weekend. This was my first time dining in an Australia's home. Elizabeth prepared plenty of wonderful food, which thoroughly we enjoyed. Most notably, we heard many stories from Rodney about the key figures and discovery in mathematical physics. I also received some nice reference and a book which encouraged me doing my own research. Of course, during my 10 years at NU, I share many exciting moments with Rodney. For example, sometime I joined Mary and Rodney for Thursday lunches, and also attending the party, hosting Chinese visitor, for example, hosting Professor Yupeng Wang, and also celebrating event like the banquet held for Professor Xiwen Guan's visit to NU. And I had once plenty time staying with Rodney during his visit to China from April to May in 2014. Rodney's first stop was arranged to visit Professor Yupeng Wang at the Institute of Physics in Beijing. I traveled to Beijing to take him and Elizabeth to Wuhan. He was to visit our institute for 4 days. Before I left, Professor Xiwen Guan and Mr. Yang treated Rodney and Elizabeth to dinner at Beijing Roast Duck restaurant near Tsinghua campus. And I was so honored to join them. At the dinner, the two great physicists talked at length about science, politics, friends, and life, etc. Afterwards, I accompanied Rodney and Elizabeth around the restaurant. It was my first time seeing him so fascinated by the statue of the cashier holding the Chinese abacus. He was curious how the bead handled addition, subtraction, multiplication, and division. He also stood long in front of the chief's statue, like wondering why Beijing roast duck was so delicious. Rodney was invited to visit Institute of Physics and Mathematics. Now our institute's name is changed as Innovation Academy for Precision Measurement Science and Technology, Chinese Academy of Science, where he gave an inspiring colloquium on his early work on the hard hexagon model. We are deeply impressed by his persistent, meticulous mathematical calculation and elegant solution. The talk was very successful. The first photo showed our director, Professor Miu-Sheng Zhang, present him with a colloquium certificate. During that period, Professor Jacques Perk and his wife, Mr. Perk, were visiting me for 3 months. In the second day after his talk, Professor Perkins Cabo and I accompanied Rodney and Elizabeth on a tour of Wuhan, including visit Hubei Provincial Museum, one of the Chinese most famous historical museum. In fact, the Wuhan area, was controlled by the state of Chu in 863 BC, and later by the Emperor Qin in 223 BC. The museum houses two very priceless treasures. For example, the Western Zhou era charm bells, which were used for making music for imperial families. And another is the sword of Gujian from the king of Yue. Anyhow, Rodney and Elizabeth really enjoyed the Wuhan culture and the visit to our institute. And to my, oh, this is too big. I should, why is it so big? I should move a little bit aside.
I think it's okay. I think he wants to move forward in the pages.
Okay. Okay. Oh, why is it gone?
It's not scrolling?
Yeah, you click. Okay. 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 Now let's move on to our my talk on the quantum transport in Hubbard model. I will discuss about the Drude and the Seebeck effect, and also if I have time and give the experimental protocol. Due to the time restriction, I should quickly to complete my talk. As you know, Hubbard model is a paradigm of physics in condensed matter physics. It's describing the model is describing the electronic property band magnetism motor insulator. In particular, it also has become increasingly important in ultra-cold atom quantum metrology, quantum information, and non-equilibrium physics. In recent years, there are many publications focusing on the property of Hubbard models. As we know, the one-dimensional Hubbard model is a typical exact solve model. The Hamiltonian, including the Hoping term on site, the C and the C dagger, it's the annihilation and the accretion operators of electron or fermions with a spin A at site J. Usually we consider the Grant canonical ensemble for studying the macroscopic property. The important thing, the model has two SU2 symmetries, the Hamiltonian commute with the SU2 algebra, spin algebra, and also the eta pairing symmetry. These two symmetry characterize the fractional spinons and the holons. It's important for us to understand the low energy physics. The Bethe equation already derived in 1968 by Lieb and Wu. And the quasi-momentum Kj, J can be 1 to n. N is total particle number, and coupled to the spin rapidity, the lambda L. Important to remember that the Bethe equation emit 3 types of Bethe root: the real quasi-momentum of the electrons moving on lattice, and also the spin lambda string. This is the spin wave bound state, and also the k lambda string. K lambda string show the length n. K lambda string show the 2n electrons form the bound state. All those states make a contribution to the quantum transport, depending on the temperature scale, how large the string length. At zero temperature, the phase diagram is already noon, and have 5 phases. The phase 1 is a vacuum. The phase 2 is partially filled and full polarized phase. 3 is half filled, full polarized. Importantly, the phase 4 is partially filled, partially polarized, and 5 is the mutter phase. And at low temperature, we can conceive the universal behavior. For example, we can use the dimensionless ratio, for example, Wilson ratio sensibility over specific divided by temperature T. This gives the constant. Different phases, we can find a different constant. We see in the phase 4 is depend on spin Latin parameter and the crossover Latin parameter, and also the spin and charge sound velocities. And phase 5 just depend, the ratio is approximately equal 8 Ks. Ks is the spin Latin parameter. Anyway, the quantum transport is very important and the hard topic. For this model, only special case people derive the, for example, the Drude weight, and in this model we can have, we can impose 3 types of gradient. As we know, the intensive quantity, if we have an intensive the gradient of intensive quantity, then we lead to the intensive density current. And this 3 gradient lead to the charge, spin, and thermal current. And we can have the full conductance matrix, and showing the spin, okay, the charge conductance CC, and the spin conductance SS, and the thermal EE, and also the crossover the conductance, for example, CS and SC. It's interestingly, we also can calculate the Seebeck effect in charge and spin degree of freedom. And the Drude weight, particularly interesting, we can obtain it from the real-time equilibrium current correlation function. And this correlation function usually is hard to derive. But anyway, if we can calculate it, then we can extract the Drude weight that describe the long-time ballistic transport behavior. And also the regular part give the diffusive part of, for example, different type of diffusion. And now in this model, we in fact we use the Cohen formula. We induce the flux for spin and charge degree. Because this model has 2 U1 symmetries, so we can impose the flux of the phase far up and down. And then the Hamiltonian also can be exactly solved. Then the Bayes-Ansatz equation involve these 2 phases, flux phases. And we rearrange it. We can let phi up equal phi down equal phi C for charge flux. And the spin is up equal minus phi down is equal phi S spin. Then we can get the linear Drude weight from the curvature by the second derivatives of energy with respect to these 2 spin and charge flux phase factor. And we can obtain the Drude weight CC and SS, and also high order Drude weight can be calculable. But anyway, the important thing, through the finite size correction, we can get all different type of Bayes-Ansatz root, the infinite size correction, up to the 3rd inverse of the 3rd order of length. Those finite size correction, then we can give a very unified formula for the Drude weight. This form. That's the important expression. In fact, this part only depends on the X gamma 1. Gamma can be K and lambda string and K lambda string. This only depends on the one, because the higher order is also related to the coefficients of the 1 over L. And so this let us write the Drude weight, linear Drude weight. Then we find we can give in this form. This form already used in generalized hydrodynamics. Here now we find the close relation between the dressed charge and the finite size correction. But it's an important way we can get the all the dressed charge in terms of the big matrix B in this convolution form. The convolution form, the QR prime is the Baird dress charge. If we can work out the Baird dress charge, then we can immediately get the dressed charge. Then we can get the Drude weight. Also, we can get the higher order Drude weight. The difficulty coming from the bigger matrix. This depends on the length of the string. Very, very big matrix. It depends on your temperature, how large the string you consider. And due to the time restriction, I do not think I have enough time. For example, we just give the Baird dress charge for particle number, magnetization number, and energy for the different Bison's root, K and K lambda string, K lambda string here. Then we can, for example, the simple is case T equals 0. We can get the dress charge equation is just we can write down in a 2x2 matrix form. It's explicitly given in this form. But importantly, this gives us the calculation of all the conductance, the Drude weight. For example, we calculate the charge Drude weight, spin Drude weight, and the crossover Drude weight. From this the numerical calculation, and show that the Drude weight can map off the phase diagram partially. For example, the CC can map out the phase 2 and 4, and could not distinguish 3 and 5. But the spin Drude weight can map all the 5 phase diagram and show an non-analytical singular behavior of Drude weight at the phase boundary. And at final temperature, of course, we can using the sum field expansion get a closed form. But anyway, people rarely to get the result for the crossover. The mission, this is the mission part in the study in the previous studies. And we know the personalization result, the charge Drude weight and spin Drude weight given in terms of the Latimer parameter and the sound velocities. For example, this is for charge for the sound velocity VC and KC. This formula, in fact, does not hold for arbitrary filling factor or magnetic field. So the general form we derive analytically in this form. This gives the 0 temperature, the Drude weight. All of them, there is 2 terms. The mission term is regarding the crossover Latimer parameters. And we can obtain this crossover Latimer parameters from the dress charge, give the exactly connection the Latimer parameter to the dressed charge. With this equation and also with the previous convolution equation, we can work out all the Latimer parameters. You can see, for example, for fixed magnetic field, we change the chemical potential. Then we can find all those different Latimer parameter has a sudden change at the phase transition point. So that's why the Drude weight has a singular behavior. We will calculate the scaling, universal scaling function for the Drude weight at quantum criticality. Another important thing is Drude weight display a counterintuitive feature of spin charge coupling rather than spin charge separation. For example, the charge and spin Drude weight consist of two terms. If we consider the repulsion very strong, then the sound velocity goes to 0. However, in this case, the charge Drude weight goes to a constant depending on the filling factor Nc. But the spin Drude weight does not go to 0, except the m equal 0, i.e. the balanced case. If the magnetization not equal 0, the charge, the spin Drude weight go to a constant is m square times sine pi Nc. Nc is the filling factor. So that's the important thing. Provide in future a rigorous measure the external the magnetization, because magnetization is can map to the magnetic field. But anyway, this means once we have non-half filling, less than half filling, and also have magnetization, then the Drude weight, spin Drude weight not equal 0. And also we get exact formula. For example, the universal scaling formula for the Drude weight at the phase transition. And due to the time, move to the next part, the spin Seebeck effect. As we know, the Seebeck effect is a very important quantity for studying the thermal sensorium or behavior. That means if we have the system, the electrons or free electrons or the metals, if we have a temperature gradient, then will lead to the charge current between the 2 points of in the system. Similar can happen in the spin. The temperature gradient can lead to the spin current due to the variation of the temperature. And here we also can, using our general formula, to calculate the spin Seebeck and the charge Seebeck effect. With our previous expression, general expression, that's a very easy way to obtain such a kind of thermal conductance and Seebeck effect. And for example, we just get the spin Seebeck effect. This is the spin Seebeck effect and for fixed magnetic field. And we change the chemical potential across the phase 2, 4, and 5. Then we note that different from the charge spin Drude weight. Here is show the divergent, I mean the accumulation of the Seebeck effect. The scaling of the spin Seebeck effect is the same as the time temperature time entropy. That's why they had the spin Seebeck effect has this accumulation at the phase transition. And okay, I will finish very soon. And also we have an inversion point. The spin current due to the temperature gradient has inversion, different direction. Why this happened? We check because the spin Seebeck effect. I mean the contribution from the spin and the charge to the spin Seebeck effect has different has opposite contributions. That's why it has inversion. And maybe I give up the Seebeck effect for the charge degree of freedom. But anyway, I'm not sure you are interested in the experimental proposal for measuring such transport behavior. Recently, there are many very nice papers for studying the quantum transport, in particular using the ultra-cooled atom, and published in Science, Nature, and PRL, and also they checked the spin conduction and the spin diffusion, and also KPZ dynamics, so many. But here we also can prove the flux is hard to be realized in ultra-cooled atom. However, the constant force can be realized in experiment. So we demonstrate if we using the constant, we added some constant potential force potential, then we can this potential very weak. Then we can get the Drude weight, which coincides with exact solution result. So that's why we can propose proposal for experimental to test this spin and charge Drude weight and the Seebeck effect. The conclusion is the following: we have rigorous obtain fundamental rule of spin and charge weight, Drude weight at zero and low temperature, showing intrinsicate interplay between the spin and charge collective motions. We have built up exact relation between Luttinger parameters and the Drude weight. We also uncovered the spin charge Seebeck effect in thermal conductivity. And my collaborators are Jia Luo, previous of my PhD student, one of my previous PhD student, and now he is a postdoc in Germany, and also Sakarika Basak, also a postdoc in USA. He graduated from the Rice University, and Professor Hanpu, my collaborators. Thank you for listening. Hello?
Hello, yes, thanks for a nice talk. And also touching on Rodney and Elizabeth's time there in Wuhan. So,
Okay.
Any questions? Andreas has a question.
Oh, Xiwen, I have a question.
Yeah.
Dependence of the Seebeck effect, spin Seebeck effect on the Hubbard propulsion U. You show, yeah. Here you see the dependence on the chemical potential. It's rather non-linear. How does it look with regard to the dependence on Hubbard U? I mean, is it a monotonous dependence, or is there an optimal value of the coupling U for the Seebeck effect? I mean, for maximal Seebeck effect?
Yeah, first, greeting. That's a very interesting question. In fact, any interaction-driven behavior is harder to derive. We in our previous paper published in Report on Progress in Physics, that's very long paper. We studied the interaction-driven phase transition. I do believe we can calculate the Seebeck spin and charge Seebeck effect driven by the interaction U. So, but it's harder than this calculation, than the calculation for the spin Seebeck effect.
Okay.
But I don't know how the Seebeck effect driven by interaction look like. But the feature could not change. Definitely, any external potential change lead to the Seebeck effect has enhancement at the criticality, because the scaling, that's the general proof, the scaling proportional to the time to the temperature time S. I also noticed your nice paper on arXiv. You showed that the particle current, no matter the temperature how high, is always ballistic. That's a nice proof. In fact, in our expression, also get the similar result for the charge degree of the multi-component fermions.
Thanks.
Okay, thanks, Andreas, and thanks again, Xiwen.
Okay, thank you, Mary, for sharing, and so look forward all of you to coming to coming to Wuhan in this November. If anyone you do not receive the invitation, you like to come to Wuhan, please write to me. And also Mary, and also Professor Nepomniachtchi, also the organizers. Thank you, and Professor Wang also include.
Okay, thank you very much.